All right. Hi, everybody. My name is Laura Patton, and I'm the head of government affairs for Springer Nature for the United States. I'm happy to introduce today's Science on the Hill event on behalf of Springer Nature, Nature Portfolio, and Scientific American. But before I turn it over to Scientific American, I just want to say a few words about why we at Springer Nature think events like these are so important. One of our objectives as a company is to be a connection between the world of science and policy and to make sure everyone benefits from the findings, knowledge, and insight that the research community generates. So we're hoping that today's panel can make a valuable contribution to that goal, and we very much appreciate the panelists have taken the time to travel here for an in-person conversation with all of you. So now let me turn it over to our moderator today from Scientific American, Clara Moskowitz.
Hi, everybody. So I'm a senior editor at the magazine for Space and Physics, and I'm happy to introduce our wonderful panelists today. Next to me is Nima Leclerc. He's a research scientist at the federally funded MITRE Research Center in Boston, where he leads an effort focused on quantum sensing. Next to him is Eric Rescolra, who is the former chief technology officer for the Firefox browser at Mozilla, and he's contributed extensively to many of the core security protocols that we use on the internet. And Zaira Nazario is a quantum theorist and the director of mathematics of computation at IBM. So we're going to do some questions as a panel, and then we'll open it up to audience questions. So start thinking of what you want to know. Eric, we're going to start it off with you. So today's data and communications are largely secured using an encryption method called public key cryptography. Can you just explain to us how that works?
Oh, we'll try. So I think it's easy to think about like what happens when you go to like a web page when you connect to Amazon or something to buy something, right? So what do you need? You need to be able to send data that nobody else can read, and you're talking to Amazon, so you're not sending it to the attacker. You're not sending it to someone who's going to steal your credit card, right? And so the way this typically works is you use these public key techniques to authenticate Amazon and to establish a cryptographic key, which you then use to encrypt the rest of the data. And this is for technical reasons, which is the public key techniques are comparatively slow, and what they call the symmetric techniques are very fast, but they don't allow you to do any of the fancy stuff you can do with public key techniques. So you might hear me say symmetric versus asymmetric. Symmetric is the fast stuff that doesn't do anything fancy, and asymmetric is the public key stuff. The public key stuff is all based on a relatively small number of mathematical techniques. You might hear someone say factoring or discrete log or elliptic curve. These are all sort of a set of mathematical techniques. All of this is based on the same basic underlying math, both the key establishment part and the authentication part. And the authentication part also goes by the name of digital signature. So I think maybe that's the place to start, I think. One more thing I guess I'll say is that the symmetric stuff is largely not implicated by quantum computers, but the public key stuff, yes.
So this current encryption method works really well against the classical computers that we have. We're okay at the moment, but with quantum computers on the horizon being developed as we speak, we're in danger because this current encryption public key is not going to hold up against them. So Zaira, what is it about quantum computers that's going to allow them to bypass this public key cryptography that we have?
Yeah, I think probably a good place to start is comparing them, what each of them are good at. You think about classical computers that are based on CPUs, they're very good at arithmetic, right? Those that are based on AI accelerators, like GPUs, those are very good at linear algebra, like matrix type of computation. So quantum computers are exceptional at finding correlations and relationship between variables, and that makes them good at finding hidden patterns, at finding global properties. So Eric mentioned factorization, like the factoring problem that is at the core of the RSA, asymmetric encryption. So if you think about that problem, not as a problem of multiplying combinations of numbers to try to find the one that gives you the original number, but instead think about it as a different problem, as the problem of finding how often a pattern repeats in a sequence of numbers. So that's the point here, right? Like the point is that problem, the factorization problem, has a very special structure. It has a sequence that repeats. And if you find the interval at which that pattern is repeating, then based on that, you can find the numbers that you're looking for. Because and you have to do this for different sequences of numbers. That interval is called a period, and it just happens that that period divides a number that is proportional to the product of the factors. So a quantum computer is very good at finding that period because it finds that pattern. It's kind of like a mathematical interferometer of sorts, if you think about it. And it works because what you're trying to find is a global property, right? It's a global property of all the numbers in the sequence taken together. And at the end of the day, the quantum entanglement that quantum computers use to operate is a global property. It's a global property. It's a property of a system of more than one particle considered as a whole. So that's what makes them so good at these type of problems.
So we're going to need entirely new problems once we have quantum computers that are not easily solvable. And that's what people are working on. And we're currently in a race to develop the quantum computers. We've got companies, we've got universities across the world racing to do this. So Nima, tell us about some of the different kinds of hardware people are using to develop quantum computers and what sorts of hurdles they're going to need to overcome to get to this point of being able to break cryptography that we have.
Yeah, it's a great question. So there are a variety of platforms out there that you're probably seeing. Different players like Google, IBM, PsiQuantum. Unlike classical computers that we have today, we haven't yet agreed on a fundamental mode of hardware or like a fundamental unit of computation for these platforms. And taking like PsiQuantum versus an IBM, they're two fundamentally different types of they use two fundamentally different types of units for computation. In one case, you're using particles of light or photons and trying to do what's called heralding to basically route those photons on a chip and have them talk to each other and generate these entangling gates. And then, very large entangled states. Whereas in the case of superconducting qubits, you're using, rather than an individual photon, an individual superconducting device that you could control with an external voltage and also microwave sources. But the thing that you're controlling there is a matter-based qubit rather than a photon-based qubit. And these all have their different challenges that we need to deal with. Photons are really good at being resilient to their noise and their environment. But that also makes it really challenging because you want these photons to talk to each other to do useful computation. And on the other hand, with superconducting qubits, they're really good at interacting with their environment. And because of that, they're really good at interacting with each other. But that's also a problem because they always want to interact with their environment. So you're trying to strike this balance. And I think to get at where do we want to be in 5, 10, 20 years, to solve useful encryption problems or also useful quantum chemistry problems, you really need to get at this million qubit, physical qubit regime. And as a hardware person, I like to think of how can you build that system from the bottom up? There are many challenges. You need to, one, have these talk to each other over very long-range interactions. So that requires new networking-based approaches where you could basically put lots of boxes together with different qubits and have those processors talk to one another. That technology is still it really hasn't been proved out yet. The other challenge is in making these systems as small as possible, which requires us to implement. One consequence of that is that we need to implement these gate operations or these individual computations with very low error so that they're not prone to noise in their environment. So another challenge is how do you control these systems in a way such that you're routing photons and microwaves in a way that is resilient to noise. So there's still a long way to go to hit that million of qubit regime. And it's an exciting time to work on it.
Quick follow-up, Nima, just so we want to get to the point where we have quantum computers with 1 million qubits. What are we at now?
So right now, we're at the 1,000 qubit regime, somewhere around that. But there's an important distinction where you have like 1,000 physical qubits, and you'll hear this a lot. There are physical qubits and logical qubits. A logical qubit is what you will actually use to do your computation with from, at the level of algorithms and software. Whereas a physical qubit is something like a transistor. It's an atom or it's like a photon. And right now we're around 1,000 physical qubits, logical qubits. We want to be, so the reason why we need millions of physical qubits is because we want to implement thousands of logical qubits. So there's this challenge of like, okay, you could put lots of qubits on a chip, but not all of those are useful because a lot of them are used as overhead to correct for errors. So that, I'd say to just directly answer that around.
I'll add a little bit of color to that because we were
Yeah.
talking about it on the sidelines.
Yeah.
That number of physical qubits that you need is very strongly dependent on the error correction code that you're using.
Yeah.
So he's quoting something for what has been so far the leading candidate for error correction code, that's the surface code. Recently, there has been discoveries of codes based on low density parity checks, or LDPC code based. And those families of codes have been shown to be 90%, need 90% less resources than the surface code, right? So that community is moving to finding very efficient codes as compared to, the reason the surface code needs so many qubits is because it's a very inefficient code in terms of like the encoding rate. It scales horribly. But people have been finding these much better LDPC codes that have been like dramatically lowering the overhead of what you need to build a computer of that size.
So essentially, it's only a matter of time until we have these machines. People call this Y2K, years to quantum. So obviously, nobody knows the future, but I'm going to ask each of you to throw out a number. If you had to take a guess or an estimate about how many years to quantum do we have left?
I think, it's important to set that target. I'd like to think of the target as being utility scale, where you have something that's useful. We have quantum computers today, like I mentioned. I'd say at least 10 years until we get to something that is utility scale. But that's my personal opinion.
All right, so I'll point to two things. Back in 2018, in one of these updates that NIST used to put as part of their standardization program, they quoted a study that was estimating that we potentially could have cryptographically relevant computers within 15 years. Right, so that was 2018. 15 years from 2018, we're looking at 2033. So that's one thing there. Whether and look, like this is just one data point. Different people have different estimates of whether that seems reasonable or whether it is like much farther out. But the second thing that I will point at is just look at the roadmaps of the quantum computing vendors. And granted, Nima mentioned this, and he's correct, depending on the modality of qubit that you're focused on, your roadmap is going to look different, and the technologies are at different stages of maturity. But in security, you always want to go by the most aggressive scenario in order to avoid pretty terrible surprises, right? So take those. And those, I would say that they are in agreement, pretty much, that we will have large-scale, fault-tolerant quantum computers by, around 2033, that day that NIST quoted back in 2018. Now, I'm not saying that those will be at a large enough scale that they will be able to break encryption. Not at all, right? Like it's not going to be there. But if you look at the rate of progress and you take those roadmaps and you look at the execution of the roadmaps, I think you can get a pretty good idea so that you can draw your own conclusions there.
So, you mentioned some pretty terrible surprises could be on the way. Well, why is this such a problem that everybody here should be thinking and worrying about? Eric, tell us what happens when we reach this point that quantum computers can break our encryption? What happens to the currently stored data, and what happens to operations that need to be secure?
Yeah, I mean, it's bad. I mean, if you believe that you have these devices and there's a range of accessibility devices from it's available to nation state attackers to you can buy it on Amazon. But if you get to the point where it's commercially feasible to do, then effectively everything you have now doesn't work. Every piece of communications that is secured now is insecure. So that means that anything you send over the internet, today and also like last year, is now vulnerable to anybody who captured it and tries to decrypt it. And going forward, your communications with anybody basically are vulnerable to active attack. I want to differentiate those two. But the technical term here is what people call harvest now, decrypt later. Yeah. It's the impersonation attacks on authentication only work at the time you have the quantum computer. But the attacks on confidentiality, the attacks on data transmitted in the past, apply to anything which happened in the past. And so, even in the best case scenario, if you imagine that we flipped the switch today and changed over to full quantum resistant algorithms, we still have 25 years of internet communications, all of which are vulnerable to attack and cannot possibly be rolled back, right? So that's a very sort of serious set of problems, obviously. And I think we'll be talking more about what people can do to actually change the situation and what is happening. But there's just no way to go back in time and fix the change that we have. And the one more thing I would add about that is, in many cases, authentication will also be implicated, even in settings where you would think of this confidentiality, because a huge amount of our authentication infrastructure actually is based on confidentiality. And the easiest way to think about this is, how do you authenticate to Amazon or to Facebook or whatever, or to or even to Gmail? And the answer is not that you use some cryptographic key. You may have a PIV card, but it's not what you use to connect to Amazon. And actually just type in a password or use a credit card number, and those things are gone, right? And so, you have to change all your passwords and all your credit card numbers. And so, even if you imagine that we fixed the system now, we have a huge overhang that has to be corrected. So, that's why it's so important to start changing things now. And so there's some hope that if we start deploying quantum resistant encryption today, then by the time we actually have a quantum computer, at least some of the sensitive information that is being exposed now will not have value later. Obviously, there's still plenty of data which has value for 20, 50, 100 years. Your medical data, national security secrets, that kind of stuff. But at least, hopefully, a lot of the commercial data will no longer have substantial value by the time this kind of attack actually becomes plausible.
So we need new cryptography. We need something new that's going to stand up to these quantum computers. So Zaira, what is that going to take? How do you develop quantum-resistant cryptography? What kind of problems are that quantum computers can't solve that classical computers can?
Yeah.
Or reversed.
Look, I think that when it comes to encryption, it's probably fair to say that any cryptography will tell you that no cryptographic scheme is 100% unbreakable. But for the most secure ones, those are based on classical algorithms. And so the goal here is to find a problem that is so hard to solve, both for a classical computer and for a quantum computer, that it becomes impractical to break, really, right? And that's not that easy, but it's also not that hard. If you think about this NIST competition that I mentioned, in the first round that lasted about 7 years, people submitted more than 80 of those candidates. By the end of the process, only 4 survived after some very intense, an immense amount of scrutiny and testing. But but look, it's and in fact, like I should mention, the ones that survived are based on essentially like solving a system of linear equations where you add some noise to them, and that's a problem that you can reformulate as a mathematical problem on lattices, on grades of point. There is a second tranche of algorithms that is being evaluated right now by NIST. So I would say that it's really not inconceivable that over the next few years, we're going to end up with about like 8 or 10 of these post-quantum cryptography algorithms.
And are some of these already being put in place?
They are, yes. I mean, people are already like starting to migrate to that. I mean, I can only speak for like my own experience, right? At IBM, we already moved, we already implemented it in our in our cybersecurity protocols. Our mainframe, like the latest, starting from C16 and now Z17, like for all those clients that use mainframe for transaction processing, that system is completely protected with this post-quantum cryptography algorithm, what we call quantum safe. And we're working with a lot of institutions, helping them do that migration to quantum safe algorithms.
I could add a little more color on that too.
Yeah, sure.
So, I mean, Zaira says, last summer just standardized basically 3 algorithms. One key exchange algorithm based on lattices, one signature algorithm based on lattices, and something we probably won't talk about here, which is a signature algorithm based on hash algorithms, which is not really practical for most uses. So what you're seeing is that the SDOs, standard development organizations that run most of the internet protocols, largely IETF, but also other organizations, are rapidly moving to deploy the key establishment algorithms, what's called MLChem, in their protocols. For technical reasons we can talk about it in a little bit, the signature algorithm deployments are dragging, both for some real technical reasons, but also because it's less urgent because of this time inconsistency I talked about earlier with harvest now, decrypt later. And you're also seeing deployment of those algorithms, both not only in standards but also in real deployments. So, for instance, on the web, Chrome and Firefox and probably Edge all do post-quantum, will offer post-quantum by default, and you see servers starting to deploy it as well. So, like I was just looking up this morning, I think Cloudflare is reporting about 13% of their traffic is post-quantum, but that's actually a kind of an underestimate because, like a lot of bots don't do post-quantum. You don't really care what the bots do. These deployments are almost all happening in what's called a hybrid mode. And what I mean by hybrid mode is you don't throw away the old classical algorithm, but you run the classical algorithm together with the post-quantum algorithm. And so why do you do that? It's obviously slower and takes more bandwidth. So why do you do that? And the answer is that, as Zaira said, you want to have something which is secure against both classical cryptanalysis and quantum cryptanalysis. And we know that the traditional algorithms are not secure against quantum cryptanalysis, but we have higher confidence to secure against classical cryptanalysis. And so what nobody wants to have happen is in 3 years to discover MLChem isn't secure. We don't have a quantum computer yet, and now all this data is insecure. And so people are instead deploying in a configuration, largely it's an industry, in these hybrid dual configurations together. So like the worst case scenario everyone thinks is like it turns out that the post-quantum algorithms are completely insecure. We're back to where we started, as opposed to things are worse. There is, I think, in some government settings, there's more emphasis on doing pure post-quantum. So like CNSA 2.0 is like largely pure post-quantum, I think. But in industry, it's largely being done in this hybrid mode.
So the race is definitely on to develop these machines as quickly as possible. Whoever does is going to have a major advantage. China, many other countries are actively working toward these machines. So Nima, how prepared are we from a supply chain perspective, from a workforce perspective for this quantum future that's coming?
Yeah, so like the semiconductor industry, the quantum industry and what it takes to build a quantum computer is very much dependent on these intertwined supply chains. And that's because you're looking at a full system stock. I'll go from the bottom. So start from the bottom. So you need to source out new materials. So there's a high dependence on rare earths when you're trying to grow these materials in the lab. I'll give you a concrete example. PsiQuantum, that's a very prominent quantum computing company taking this photonics-based approach, relies on these switching materials that allows you to change the phase of photons as they're routing through a chip. That material that they landed on it requires barium, it requires titanium, and it requires other precursors that are like don't always exist in the U.S. You need to like source that out from other countries. So just from like a materials perspective, we need to be better about one, identifying materials that may exist within the U.S. or like we're not dependent on an adversary to acquire those. But also we have the supply chains to actually like grow those materials in the U.S. That comes to another thing that you need to rely on the semiconductor industry to make these processors. All of the control electronics that goes into manipulating these qubits are all based on classical semiconductor technology. They're based on microwave technology, as well as like lasers. And currently, these supply chains are, very much intertwined across many different regions of the world, which is not a problem, but it's something that I think as we're trying to assert dominance and technology within the U.S., we need to consider this aspect, like where are we getting most of our microwave components from? Where are we getting most of our barium titanate from, or whatever like other like maybe exotic superconducting material? Fortunately, a lot of the superconductors that are used for these Josephson junction devices at IBM are pretty standard aluminum. But the maybe just to speak a bit more, I'll add one other point about supply chain. A lot of these systems need to be cryogenically cooled. The thing that allows you to go down to near absolute zero, down to millikelvin temperature, is this dilution, what's called dilution cooling process, where you need to mix helium-3 and helium-4. So it's actually really difficult to get helium-3 because it's a byproduct of a nuclear reaction. And the DOE holds a stockpile where I've had to go through this process myself, where you'll buy like a $50,000 canister of helium-3 that you'll hook up to your dilution fridge. And that acquisition process takes such a long time because it's so hard to find. So how do we synthesize that in a more scalable, reliable way? To speak to workforce, I think we're fortunate that apart from the quantum aspect of building a quantum computer, much of a quantum computer is actually classical. It relies on lasers that we already know how to build. It relies on microwave engineering. There's also like a software layer to it. So there's a lot of talent that we could rely on that already exists. And we need to just provide more incentives, like as this industry grows, to make quantum, pursuing a career in quantum technology more attractive to people who have talents. I'm a physicist, but I rely a lot on FPGA engineers who know how to do like this really advanced low-level programming that's used in embedded systems, because it turns out that that's sort of what we need to be able to miniaturize a lot of the control electronics in a compact system and like do a lot of these like control protocols on the fly. But then I think, of course, like the other thing is like at the PhD level, we need to also, like, companies need to be more open-minded as to, like, recruiting people from all sorts of disciplines, because as I noted, like a lot of the innovations that you're seeing are very interdisciplinary. Like the reason some companies are able to sort of scale up their neutral atom-based approaches relies on integrated photonics that requires like a PhD in integrated photonics. Another aspect, and then lastly, K through 12. I think just like this is my own personal experience. I grew up in the Berkeley area, and just what got me into science and really excited about like eventually pursuing a career in quantum technology is just being around like Lawrence Berkeley National Lab and seeing the advanced light source and interacting with scientists. So like I think there's a lot of good work out there, but I think there still needs to be yeah, there's a lot of work to be done in just like incentivizing people to go into the sciences in general, because like I said, it doesn't really matter if you do a PhD in electrical engineering or chemistry. Like all of those are useful as we build up a quantum workforce.
So, Zaira, if you want to talk a little bit more about, you mentioned how we're already switching over to these post-quantum algorithms, but what else needs to be happening? What else could individuals, companies, organizations be doing to prepare for this future?
Yeah. I think the first step is start planning. I mean, organizations should have started planning like yesterday. The clock is ticking here. Right? So I think that's number one. So how do you do that? We recommend starting by building a roadmap and a readiness plan, if you will. So start from there. Incorporate this quantum safe or post-quantum, cryptography into your existing cybersecurity strategies. Start doing things like assigning responsibilities in your organization, setting timelines, allocating the budget that would be needed to do these migrations. And then in terms of acting, organizations can start by building an inventory of, the digital assets that, you can start by doing it in very specific areas that the organization prioritizes. And that inventory should include also dependencies and all those vulnerabilities. And that will help them to prioritize which of those digital assets to migrate first based on risk. And then, use one of these algorithms that NIST has selected and start doing that migration. Other things that they can do, things like establish a center of excellence, that can help to start preparing the organization. And none of this would be possible if they don't start training the necessary resources to do all of this. So I think those are some concrete steps there and ideas for how different organizations can go around doing this.
Yeah, Eric, do you want to add to that?
Yeah, I think that there are probably, that sounds very scary to many organizations. I think I would say they're at a very high level. There's a spectrum of organizations of sophistication and but also fortunately of complexity. Mm-hmm. And if you're an organization which has deployed a huge amount of your own cryptographic technology, you have to really be studying this very substantially. The good news is there are a number of organizations which really just have off-the-shelf technology. They just use TLS, or they just use they just use WebRTC, or they just use SSH or whatever. And those people largely what they have to do is get the newest version of the software and turn on the right knobs, right? And those people kind of have to be paying attention to
there are open source tools
exactly,
that can help you do that.
Exactly so, right? And so what many organizations need to be doing is they've allowed themselves to fall behind, and they're well, I'm on version 2 and everyone else on version 7, and this version is 8 years old, and those people often figure out how to upgrade. And so organizations which have allowed themselves to be in that situation need to be moving to the latest versions of the software they're already using, so that when those things turn on post-quantum, they can just flip the switch, and it's not a big forklift upgrade, right? So I think I think that the good news is many people will just get things for free if they stay in the latest version. But if you're not in the latest version, you're going to be in real trouble. The second thing I would add is that in many cases, you have to be looking at what assets are already been compromised in this harvest now decrypt later situation, and be looking to roll those assets forward. So again, if you make very extensive use of passwords, I need thinking about how to move those passwords off of, how to rotate every single one of those passwords, one kind of vulnerability. But I'm hoping that in many cases you won't have to be thinking about MLChem or MLDSA, because that part you'll get for free. What you have to do is all the fallout from your years of exposure to quantum computers that you have to fix.
Yeah.
Mm. So as this is happening, we're also living through this AI boom that's going on. So how do these things intersect? Nima, is it likely that AI is going to be used to develop or operate quantum computers?
Yeah, no, I'm glad you asked that question. I was just at this conference about a month ago called AI for Quantum, hosted by Novo Nordisk over in Denmark. And it was, it was the first conference that I've seen that was entirely centered on this topic. How are you using AI to accelerate quantum? There's another direction, which I can't speak, probably Zaira could talk more about how do you implement AI algorithms more efficiently with quantum, I'm focusing on the first. But I think there are plenty of opportunities that we're just starting to explore, at least in like my own work, like what we're doing right now. We build quantum sensors, which are very different technologies from a quantum computer, but at a qubit level, they operate similarly, and we need to think about the same types of control and readout protocols. And as I alluded to before, we think a lot about noise. How do we want to mitigate the noise in the environment? And how can you sort of do this adaptively? And there's been advances that we're leveraging in the robotics community, and also like this is also the same type of algorithm that is actually used to fine-tune the LLMs that are used in ChatGPT, but using a class of what are called reinforcement learning models to adaptively control the quantum sensor. So you could change like the shape of the laser pulses and the shapes of the microwave pulses that you're driving your system with to cancel out for specific sources of noise. And the reason this sort of works well is because these models are really good at dealing with high dimensional data, and they're good at also working like in very noisy environments. So we're sort of going about that by constructing data sets in a very intelligent, in an intelligent way that represent the noise environment that you would actually experience in, say, some operational environment where you want to put this quantum sensor on a drone. And we're trying to train models to produce optimal pulse sequences that that work well for quantum sensing. You're also seeing this in quantum error correction codes, which I can't speak to as much, but there's been a recent high-profile Nature publication or some other Nature subjournal from Google DeepMind in generating these quantum error correction codes that and those topologies that are being used on real hardware today. Zaira could probably speak more on that. And then the last aspect that we're also exploring is leveraging generative models to generate materials that could potentially be used as better qubit materials. That's actually something that we're actively exploring right now. It's similar to AlphaFold in that it uses the same underlying what's called a diffusion model to generate sort of atomic structures of materials that have desirable properties. But we're sort of fine-tuning the architecture and changing different properties about the architecture to design for properties like long qubit lifetime, as an example. So I think there are plenty of opportunities, but part of it is I'm constantly having to keep up with all the advancements and at these AI conferences like NeurIPS and ICML, plus all of the physics as well. So I think it just takes working between the two, but a lot of opportunity there.
Thank you so much for joining us. I think we're at time, and thank you to our panelists very much.